I want to do one more paper 3 example problem because it's a little bit, there's like different styles. The one I did before was all geometric, and this one is more calculus and functions based. So, all right, we've got some logarithms here, some blah 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 about logarithms, and they want us to graph these 3 functions here. Okay, and so you can, like, please, use your graphing calculator. Don't try to be a hero here. If you graph these functions, y equals x, I hope you do know what that one looks like. Remember, you can press on the TI calculators, you can press the math button, alpha math, to bring up log of a different base. So I just did that for log base 2. The log button itself will graph log base 10. So here are the 2 graphs that I see. And then I'm going to graph y equals x on there also, so you can see how the color coding works on my screen. All right, and so you can see that. So both of my log graphs, let's make this one log base 2. And then make this one log base 10. And both of them have an intersection with the x-axis of 1, 0. Neither of them touch the y-axis. There's an asymptote there, and that's all we needed to graph. I was just double checking, reading through it again to make sure that I didn't need to graph anything else, but that was it. Great. Now we are considering the case where a equals e. All right, so use calculus to find the minimum value of the expression x minus natural log of x. So we say y equals x minus natural log of x. So y prime is 1 minus 1 over x. Finding a minimum, so we set our derivative to 0. That means 1 equals 1 over x. That means that x equals 1. Now we need to justify that it's a minimum. You could do that with the first derivative test or the second derivative test. I feel like taking a second derivative today. The derivative of 1 is 0. Negative 1 over x, remember that 1 over x is the same as x to the minus 1 power. So if we had negative 1 over x, we have negative x to the negative 1. And so that means we get positive x to the negative 2. So at the number 1, y double prime of 1 is equal to 1, and that's greater than 0. When the second derivative is greater than 0, that implies that there is a minimum value. So now we know that the minimum occurs when x is equal to 1. The minimum value is plugging in 1 to the original function, which is 1 minus natural log of 1, which is equal to 1. Okay, so we know that x minus ln x is at a minimum equal to 1. That means that x minus ln x is greater than or equal to 1. And that means x minus ln x is greater than, strictly greater than 0. Well, that means if you add ln x to both sides, that x is greater than natural log of x. By the way, if you look at your graph here, you can see that where y equals x is always above where y equals either of the logs that I typed in. That's a visual way of confirming it. Okay, now we're done with parts B and C. Part D. There exist values of a for which log base a and x do have intersection points. Okay? Then the following table gives 3 intervals for the value of a. Okay? Then there's P, Q, and R, and we're going to try different a values in those different intervals. Okay, so we're going to try an a value between 0 and 1. Let's try 0.8. Let's try an a value between 1 and 1.4. So let's try 1.2. And then let's try another one for between 1.5 and 2. Okay, so here's what you did. I just typed in a couple different logs, and we're going to see how many times they intersect P, Q, and R. So the blue, red, and pink in order correspond with the table that I'm doing. So blue, red, and then the pink comes through. Okay. So I can see that the blue and the red graph each intersect it once. It looks like the pink one does not intersect it. So going back to look at my thing, the blue and the red intersect it once. It looks like the pink one does not intersect it. Interesting. I kind of thought they intersected it more times there. Let's try varying it a little bit more. Let's see if it stays the same if I change those bases just a little bit. You know, sometimes I do something wrong. Yeah, that should be good. Okay, let's try this again. So blue, red. Oh, I missed it. Okay, so if you look at the red graph here, you can see that it actually intersects it twice. On my first one, the second intersection point was like off to the right. I just didn't see it, so it's good to double check. So it looks like the red one hits it twice, the blue one hits it none, and the pink one misses. Okay, so the blue one hits it once. The red one hits it twice, and the pink one missed it entirely. Okay. Now, let's keep going here. Consider an A value. There exists an A value such that the line y equals x is a tangent at a point P. So tangent means two things. It means that it intersects, and it means that it has the same slope, same gradient. So what we can do is take the derivative. So the derivative of that line is 1, and the derivative of the log base A of x is 1 over x times 1 over x times 1 over natural log of A, which is in your formula packet, or if you remember that log base A of x is the same as natural log of x divided by natural log of A. With that change of base formula, you can see why that's the derivative. So if we set those two things equal to each other, we have 1 equals 1 over x ln A. In other words, multiply by x, x equals 1 over natural log of A. So what this is saying is at that x value, they have the same slope, okay? But we also need that x value to be a point of intersection. So if we want two things to intersect, we set the original functions equal to each other. So we say x equals log base A of x. In other words, natural log of x over natural log of A, okay? And then what I'm going to do is plug in the x value that I'm circling over here for both my x values here. So I know that 1 over natural log of A equals the natural log of 1 over natural log of A over natural log of A. There's a lot of natural logs going on. Multiply both sides by natural log of A, and you have this expression. 1 equals natural log. How do you get rid of a natural log? You do the anti-log. You do e to the left side and e to the right side. So now what we have is e equals, when I did e to the outer natural log, that canceled out. So I have 1 over ln A. Let's multiply both sides by ln A. Remember, we're trying to solve for A. So we go divide by e, makes it e to the negative 1. Then we do it again, e to the left side, e to the right side. So we have A equals e to the 1 over e, or e to the negative 1 power, like that. That A value will make our graphs intersect and have the same slope. So find the exact coordinates of P and the exact value A. Now here's the nice thing about the point P. The point P is on the line y equals x. So at that a value, we know that the natural log we know that at that a value here, we can just put it into this expression here and we'll have the x value, which is also equal to the y value because it's on the line y equals x. So we have x equals 1 over natural log of a, natural log of a, so that's e to the 1 over e. And the natural log cancels out the e, so you just end up with x equals e, which means that y does also. Okay? So let's get rid of some of the other stuff. I just want to show you that. This is not technically necessary in the problem, but if you did math alpha math, you had a base of e raised to the 1 over e. You will see that that intersects one time at a tangent right there, and at that point of intersection, if I calculate like the value at the point x equals e, right there, it'll land it right on the curve, and you can see it's the perfect e comma e point. Okay, so then using that, we can now say what range of values will have 2 and will have no intersection points. Because this point right here is in between 1.4 and 1.5, so it's kind of getting in between this area here. So now I know that when 1 is less than a is less than e to the 1 over e, then you have 2 intersection points. And then when e to the 1 over e is less than a, then you have 0 intersection points. And that's it. Thanks for watching. Let me know if you got any questions.